In computer science, a binary tree is a tree data structure in which each node has at most two children, which are referred to as the left child and the right child. A recursive definition using just set theory notions is that a binary tree is a triple, where L and R are binary trees or the empty set and S is a singleton set. Some authors allow the binary tree to be the empty set as well. From a graph theory perspective, binary trees as defined here are actually arborescences. A binary tree may thus be also called a bifurcating arborescence, a term which actually appears in some very old programming books, before the modern computer science terminology prevailed. It is also possible to interpret a binary tree as an undirected, rather than a directed graph, in which case a binary tree is an ordered, rooted tree. Some authors use rooted binary tree instead of binary tree to emphasize the fact that the tree is rooted, but as defined above, a binary tree is always rooted. A binary tree is a special case of an ordered K-A-R-Y tree, where K is 2. In computing, binary trees are seldom used solely for their structure. Much more typical is to define a labeling function on the nodes, which associates some value to each node. Binary trees labeled this way are used to implement binary search trees and binary heaps, and are used for efficient searching and sorting. The designation of non-root nodes as left or right child even when there is only one child present matters in some of these applications. In particular, it is significant in binary search trees. In mathematics, what is termed binary tree can vary significantly from author to author. Some use the definition commonly used in computer science, but others define it as every non-leaf having exactly two children and don't necessarily order the children either. Definitions. Recursive definition. Another way of defining a full binary tree is a recursive definition. A full binary tree is either a single vertex, a graph formed by taking two binary trees, adding a vertex, and adding an edge directed from the new vertex to the root of each binary tree. This also does not establish the order of children, but does fix a specific root node. To actually define a binary tree in general, we must allow for the possibility that only one of children may be empty. An artifact, which in some textbooks is called an extended binary tree, is needed for that purpose. An extended binary tree is thus recursively defined as the empty set is an extended binary tree. If T1 and T2 are extended binary trees, then denote by T1, T2 the extended binary tree obtained by adding a root are connected to the left to T1 and to the right to T2 by adding edges when these subtrees are non-empty. Another way of imagining this construction is to consider instead of the empty set a different type of node, for instance square nodes if the regular ones are circles. Using graph theory concepts, a binary tree is a rooted tree that is also an ordered tree in which every node has at most two children. A rooted tree naturally imparts a notion of levels. Thus for every node a notion of children may be defined as the nodes connected to it a level below. Ordering of these children makes possible to distinguish left child from right child. But this still doesn't distinguish between a node with left but not a right child from a one with right but no left child. The necessary distinction can be made by first partitioning the edges, i.e., defining the binary tree as triplet, whereas a rooted tree and E1, E2 is empty, and also requiring that for all j1, 2, every node has at most one ej child. A more informal way of making the distinction is to say, quoting the Encyclopedia of Mathematics, that every node has a left child, a right child, neither, or both, and to specify that these are all different binary trees. Types of binary trees. Tree terminology is not well standardized and so varies in the literature. A rooted binary tree has a root node and every node has at most 2 children. A full binary tree is a tree in which every node in the tree has either 0 or 2 children. A perfect binary tree is a binary tree in which all interior nodes have 2 children and all leaves have the same depth or same level. An example of a perfect binary tree is the ancestry chart of a person to a given depth, as each person has exactly 2 biological parents. In a complete binary tree, every level, except possibly the last, is completely filled, and all nodes in the last level are as far left as possible. It can have between 1 and 2 H nodes at the last level H. An alternative definition is a perfect tree whose rightmost leaves have been removed. Some authors use the term complete to refer instead to a perfect binary tree as defined above, in which case they call this type of tree an almost complete binary tree or nearly complete binary tree. A complete binary tree can be efficiently represented using an array. In the infinite complete binary tree, every node has 2 children. The set of all nodes is countably infinite, but the set of all infinite paths from the root is uncountable, having the cardinality of the continuum. These paths correspond by an order-preserving bijection to the points of the Cantor set, or to the set of positive irrational numbers. A balanced binary tree has the minimum possible maximum height for the leaf nodes, because for any given number of leaf nodes the leaf nodes are placed at the greatest height possible. H balanced unbalanced. H equals 2, 1, 0. A, B, C, D, A, B, C, D, 1. A, B, C, D, A, B, C, D, 2. AB C D A B C D 3, A B C D AB C 4. AB1 common balanced tree structure is a binary tree structure in which the left and right subtrees of every node differ in height by no more than 1. One may also consider binary trees where no leaf is much farther away from the root than any other leaf. A degenerate tree is where each parent node has only one associated child node. This means that, performance-wise, the tree will behave like a linked list data structure. Properties of binary trees. The number of nodes in a full binary tree is at least and at most, whereas the height of the tree. A tree consisting of only a root node has a height of 0. The number of leaf nodes in a perfect binary tree is because the number of non-leaf nodes. This means that a perfect binary tree with leaves has nodes. In a balanced full binary tree. In a perfect full binary tree, thus, the maximum possible number of null links in a complete binary tree of n nodes is where only one node exists in bottom-most level to the far left. The number of internal nodes in a complete binary tree of n nodes is, for any non-empty binary tree with n0 leaf nodes and n2 nodes of degree 2, n0 equals n2 plus 1. Combinatorics. In combinatorics, one considers the problem of counting the number of full binary trees of a given size. Here the trees have no values attached to their nodes, and trees are distinguished only by their structure. However, the left and right child of any node are distinguished. The size of the tree is taken to be the number n of internal nodes. The other nodes are leaf nodes and there are n plus 1 of them. The number of such binary trees of size n is equal to the number of ways of fully parenthesizing a string of n plus 1 symbols separated by n binary operators, so as to determine the argument sub-expressions of each operator. For instance, for n equals 3, one has to parenthesize a string like, which is possible in 5 ways. The correspondence to binary trees should be obvious, and the addition of redundant parentheses is disallowed. There is a unique binary tree of size 0, and any other binary tree is characterized by the pair of its left and right children, if these have sizes I and j respectively. The full tree has size I plus j plus 1. Therefore, the number of binary trees of size n has the following recursive description, and for any positive integer n, it follows that is the Catalan number of index n. The above parenthesized strings should not be confused with the set of words of length 2n in the Dyke language, which consist only of parentheses in such a way that they are properly balanced. The number of such strings satisfies the same recursive description, together with the Dyke subword remaining after that closing parenthesis, whose lengths 2i and 2j satisfy I plus j plus 1 equals n. This number is therefore also the Catalan number. So there are also 5 Dyke words of length 10. These Dyke words do not correspond in an obvious way to binary trees. A bijective correspondence can nevertheless be defined as follows. Enclose the Dyke word in an extra pair of parentheses, so that the result can be interpreted as a list expression as only occurring atom, then the dotted pair expression for that proper list as a fully parenthesized expression describing the corresponding binary tree. The ability to represent binary trees as strings of symbols and parentheses implies that binary trees can represent the elements of a free magma on the singleton set. Methods for storing binary trees. Binary trees can be constructed from programming language primitives in several ways. Nodes and references in a language with records and references. Binary trees are typically constructed by having a tree node structure which contains some data and references to its left child and its right child. Sometimes it also contains a reference to its unique parent. If a node has fewer than 2 children, some of the child pointers may be set to a special null value, or to a special sentinel node. This method of storing binary trees wastes a fair bit of memory, as the pointers will be null more than half the time. A more conservative representation alternative is threaded binary tree. In languages with tagged unions such as ML, a tree node is often a tagged union of 2 types of nodes, one of which is a 3-tuple of data, left child, and right child, and the other of which is a leaf node, which contains no data and functions much like the null value in a language with pointers. For example, the following line of code in OCaml defines a binary tree that stores a character in each node. Type chr_tree equals empty, node of char *chr_tree*chr_tree arrays. Binary trees can also be stored in breadth first order as an implicit data structure in arrays. And if the tree is a complete binary tree, this method wastes no space. In this compact arrangement, if a node has an index I, its children are found at indices im, while its parent is found at index. This method benefits from more compact storage and better locality of reference, particularly during a pre-order traversal. However, it is expensive to grow and wastes space proportional to 2h, and for a tree of depth h with n nodes. This method of storage is often used for binary heaps. No space is wasted because nodes are added in breadth first order. Encodings. Succinct encodings. A succinct data structure is one which occupies close to minimum possible space, as established by information theoretical lower bounds. The number of different binary trees on nodes is the Catalan number. For large, this is about, thus we need at least about bits to encode it. A succinct binary tree therefore would occupy bits. One simple representation which meets this bound is to visit the nodes of the tree in pre-order, outputting 1 for an internal node and 0 for a leaf. If the tree contains data, we can simply simultaneously store it in a consecutive array in pre-order. This function accomplishes this. Function encoder succinct. If n equals nil, then append 0 to structure, else append 1 to structure, append n, data to data. Encoder succinct. Encoder succinct. The string structure has only bits in the end, whereas the number of nodes, we don't even have to store its length. To show that no information is lost, we can convert the output back to the original tree like this. Function decoder succinct. Remove first bit of structure and put it in B if B equals 1, then create a new node and remove first element of data and put it in n, data n, left equals decoder succinct n, right equals decoder succinct return n, else return nil. More sophisticated succinct representations allow not only compact storage of trees, but even useful operations on those trees directly while they're still in their succinct form. Encoding general trees as binary trees, there is a one-to-one mapping between general ordered trees and binary trees, which in particular is used by Lisp to represent general ordered trees as binary trees. To convert a general ordered tree to binary tree, we only need to represent the general tree in left-child-right sibling way. The result of this representation will be automatically binary tree, if viewed from a different perspective. Each node n in the ordered tree corresponds to a node n in the binary tree. The left child of n is the node corresponding to the first child of n, and the right child of n is the node corresponding to n's next sibling, that is, the next node in order among the children of the parent of n. This binary tree representation of a general order tree is sometimes also referred to as a left-child-right sibling binary tree, or a doubly chained tree, or a filial heir chain. One way of thinking about this is that each node's children are in a linked list, chained together with their right fields, and the node only has a pointer to the beginning or head of this list, through its left field. For example, in the tree on the left, A has the 6 children, B, C, D, E, F, G. It can be converted into the binary tree on the right. The binary tree can be thought of as the original tree tilted sideways, with the black left edges representing first child and the blue right edges representing next sibling. The leaves of the tree on the left would be written in Lisp as I, J, C, D, F, which would be implemented in memory as the binary tree on the right, without any letters on those nodes that have a left child. Common operations. There are a variety of different operations that can be performed on binary trees. Some are mutator operations, while others simply return useful information about the tree. Insertion nodes can be inserted into binary trees in between two other nodes or added after a leaf node. In binary trees, a node that is inserted is specified as to which child it is. Leaf nodes. To add a new node after leaf node A assigns the new node as one of its children and the new node assigns node A as its parent. Internal nodes. Insertion on internal nodes is slightly more complex than on leaf nodes. Say that the internal node is node A and that node B is the child of A. A assigns its child to the new node and the new node assigns its parent to A. Then the new node assigns its child to B and B assigns its parent as the new node. Deletion. Deletion is the process whereby a node is removed from the tree. Only certain nodes in a binary tree can be removed unambiguously. Node with 0 or 1 children. Suppose that the node to delete is node A. If A has no children, deletion is accomplished by setting the child of A's parent to null. If A has 1 child, set the parent of A's child to A's parent and set the child of A's parent to A's child. Node with 2 children in a binary tree. A node with 2 children cannot be deleted unambiguously. However, in certain binary trees these nodes can be deleted, though with a rearrangement of the tree structure. Traversal. Pre-order, in order, and post-order traversal. Visit each node in a tree by recursively visiting each node in the left and right subtrees of the root. Depth first order. In depth first order, we always attempt to visit the node farthest from the root node that we can, but with the caveat that it must be a child of a node we have already visited. Unlike a depth-first search on graphs, there is no need to remember all the nodes we have visited, because a tree cannot contain cycles. Pre-order is a special case of this. See depth-first search for more information. Breadth-first order. Contrasting with depth-first order is breadth-first order, which always attempts to visit the node closest to the root that it has not already visited. See breadth-first search for more information. Also called a level-order traversal. In a complete binary tree, a node's breadth index can be used as traversal instructions from the root, reading bitwise from left to right, starting at bit D1, where D is the node's distance from the root, and the node in question is not the root itself. When the breadth index is masked at bit D1, the bit values 0 and 1 mean to step either left or right, respectively. The process continues by successively checking the next bit to the right until there are no more. The rightmost bit indicates the final traversal from the desired node's parent to the node itself. There is a time-space trade-off between iterating a complete binary tree this way versus each node having pointer per second to its sibling per second.